Stand anywhere on Earth, look to the horizon, and ask yourself, why does it look endlessly flat? Feel the ground beneath your feet, still, silent. So how could it possibly be moving at thousands of kilometers per hour? Watch waves settle into perfect levelness. How can water curve if it always seeks a straight, steady surface? Look at the sky. Does the sun really travel across a spinning world? Or does the world simply spread out beneath a wandering sun? Two ideas, two visions of the same planet. One question that refuses to stay silent. What is the shape of the place we call home? Spherical Earth. The model that all of us are familiar with today is called the spherical Earth. Long before rockets, satellites, and navigation systems, there were questions. Questions so simple, they became revolutionary. Sailors noticed something strange. A ship didn't shrink evenly as it sailed away. Its hull vanished first, then its sails, as if slipping behind a gentle curve. Travelers moved north or south and watched familiar constellations fade, replaced by stars they had never seen. Why would the sky change like that, unless the earth changed beneath them? Then came a moment that felt like magic. In two cities, at the same hour, the sun cast two different lengths of shadow. A small difference that whispered of a world not flat, but bending ever so slightly under the same sky. Over centuries, explorers circled the globe, mathematicians refined measurements, and scientists built models where gravity pulled in all directions, not upward or downward, but inward, toward a center. To many minds, this created a picture of a world that fits together, a world curved, balanced, and woven into the structure of the universe itself. According to this viewpoint, these are beliefs and interpretations held by flat Earth researchers. Their ideas rely heavily on direct human observation, everyday experience, and strong skepticism towards satellite imagery. From this perspective, anything shown from space, photos of Earth, videos of missions, or CGI reconstructions, is not considered definitive evidence, because it cannot be independently verified by ordinary people. Their principle is simple. If we cannot observe it ourselves without intermediaries, certainty is difficult. They begin with the horizon. When looking out to sea or across a wide plain, the horizon appears perfectly straight, never curving downward on either side. Even at high altitudes, whether from planes, balloons, or drones, the horizon still rises to eye level, rather than dropping away. This raises their first question. If Earth is curved, why does the horizon always meet our eyes at the same height? Next comes water, which plays a central role in their argument. Water naturally forms a flat, level surface, whether in a cup, a calm lake, or a long stretch of ocean. They argue that no visible curvature is ever observed across large bodies of water. From this, they conclude, a surface that remains level at small and large scales may indicate flatness, not curvature. When it comes to the sky, this viewpoint suggests that the sun and moon might be much closer and smaller than commonly believed. Instead of orbiting millions of kilometers away, they imagine these bodies moving in circular paths above the Earth, like lamps illuminating different parts of a room, creating day and night through directional light rather than planetary rotation. Regarding motion, They emphasize that humans feel no sensation of Earth spinning at 1,600 kilometers per hour on its axis or moving through space at even higher speeds. No sideways force, no vibration, no physical indicator points to such motion. And so another question appears. If such tremendous movement is happening constantly, why do our senses detect none of it? In the end, this worldview relies on a central message. Don't ignore simple observations. The world may not be what we assume it to be. And it is these questions, not stubbornness, not conflict, but pure curiosity that keep this perspective alive. The horizon. One of the first questions people ask is simple. If Earth is truly curved, why does the horizon always look perfectly flat? Flat Earth researchers point out that even from high-altitude planes or balloons, the horizon neither curves downward nor drops away. It appears to rise to eye level. Scientists, however, explain that Earth's curvature is far too large for the human eye to detect directly. Only precise measurements, lasers, long-distance surveys, and high-altitude instruments show the slight dip that our vision can't perceive. Maybe the real question is, how much can the eye truly see, and where do measurements take over? Water. Another major point is water. Flat Earth supporters argue that water forms a perfectly level surface, in a cup, a lake, or an ocean. And if it's level everywhere we see it, how could it be part of a curve? Scientists explain that level doesn't mean flat. It means perpendicular to gravity. On a massive planet, that level line gently curves without being visible up close. So perhaps the debate is less about water itself and more about the scale we're observing. Motion, with the airplane example. If Earth is spinning at 1,600 kilometers per hour, why don't we feel any motion at all? Flat Earth researchers see stillness as evidence that Earth isn't moving. Our bodies sense no rotation, no vibration, nothing. But physicists point to a familiar example. In a plane flying smoothly at 900 kilometers per hour, or even at 9 kilometers per hour, you feel almost nothing when the motion is constant. We sense acceleration, not steady movement. And while we don't feel Earth's spin, phenomena like global wind patterns, the Coriolis effect, and star trails are often cited as indirect evidence of rotation. Still, the question remains compelling because motion is something our senses rarely detect accurately. Ships disappearing hull first. When ships leave the shore, their lower sections disappear before the upper parts. Why? Flat Earth researchers say this could simply be perspective. Objects shrinking until the lowest parts fall below the limits of vision. Scientists counter that even with strong zoom, the hull does not return, while the mast and upper sections remain visible, a pattern consistent with curvature and confirmed in multiple shoreline experiments. Yet the discussion continues because what we see and what instruments measure are not always the same thing. Stars and latitude. Another puzzle lies in the night sky. Flat Earth supporters view the heavens as a dome, with stars moving in circular paths above us. But astronomers note that constellations change as we move north or south, and stars in the southern hemisphere rotate in the opposite direction, a pattern that aligns cleanly with a spherical Earth but challenges a dome-based model. Still, the sky remains one of the most mysterious parts of this debate. a single canvas interpreted in two very different ways. Airplane flight paths. Another question often raised involves airplane routes. If Earth is a globe, why do some flights take curved paths instead of straight lines? Flat Earth supporters say this is because aircraft follow straight lines across a flat map, and that curved paths only appear curved because of how maps distort the world. But pilots and geographers explain that on a globe, the shortest path between 2 points is a great circle route, which looks curved on flat maps, but is perfectly direct on a sphere. Long-distance flights consistently match these great circle predictions. So the question becomes, are we seeing map distortion or the geometry of a curved world? Lunar eclipses. During a lunar eclipse, the Earth casts a shadow on the Moon. The shadow is always curved. Why? Flat Earth models offer several interpretations, including the idea of a second unseen object passing between the Sun and Moon. Astronomers, however, argue that a curved shadow appearing from every angle aligns with a spherical Earth rotating in space. This explanation has been consistent from Aristotle to modern astrophysicists. Yet the mystery of eclipses remains a powerful symbol of how differently the same event can be interpreted. Time zones. Why do different places on Earth experience day and night at completely different times? Flat Earth researchers propose that the Sun moves in a circular path above the surface, illuminating different regions at different times, like a spotlight moving across a room. Scientists argue that this spotlight sun model fails to reproduce real-world measurements, especially the sharply defined day-night terminator seen from satellites and high-altitude balloons. On a sphere, time zones emerge naturally as the planet rotates. Still, the beauty of this debate is how both sides attempt to explain the same daily cycle we all experience. Satellite technology. What about satellites? GPS, weather forecasting, global communication, all depend on objects said to be orbiting Earth. Flat Earth supporters argue that satellites could be high-altitude balloons, ground-based towers, or alternative technologies, and that the orbiting satellite model is not directly observable. Engineers and physicists counter that satellite orbits match precise mathematical predictions. Signals, delays, coverage patterns, and geostationary positioning all behave exactly as expected around the rotating sphere. But again, the core tension remains the same. Do we trust what we can observe directly, or the technology built from complex models? The edge. One of the most well-known questions is this: if Earth is flat, where's the edge? Some flat Earth models describe a vast ice boundary surrounding the world, not as a place to fall off, but as a natural barrier humans rarely explore. Scientists respond that expeditions, polar flights, satellite imagery, and global navigation show no evidence of such a boundary. Instead, every direction you travel eventually loops back, a signature of a spherical surface. Still, the idea of an edge captures imagination, not because it is proven, but because it touches something ancient in the human mind, the desire to know what lies beyond the maps. For thousands of years, people have tried to understand our world, its shape, its motion, its place in the universe. Today, measurements, navigation, and physics point strongly toward a curved Earth, a model tested by sailors, scientists, satellites, and centuries of observation. Yet, even with all that evidence, questions continue to surface, because curiosity never fully disappears. And maybe that's the point. The story of our planet has always grown through questions, not silence. So now it's your turn. What do you see? What makes sense to you? Which ideas deserve more exploration? Share your thoughts below. Not to choose sides, but to keep the search for truth alive. Bye for now.